First problem here, we're just looking for the regular old derivative. So this is going to be a chain rule problem, and we will let u, then du dx is 3x squared plus 1, y is u to the 3 halves, so dy du is 3 halves, u to the, nope, not 1/3, 1/2. And then if we multiply those together, that would get us this, which I am going to rewrite with a radical. Okay. Reason I wanted to rewrite that with a radical is because now it's going to say 1b. So now it says find the antiderivative of this. So notice we've got 3x squared plus 1, 3x squared plus 1. We've got the square root of x cubed plus x. The only thing that's different is this coefficient of 3 halves. So the antiderivative of this function is going to be this, just with a coefficient to negate this 3 halves. So for 1b, the antiderivative is going to be that. This 2/3 being the factor that would negate that 3 halves. And we're just, again, when they use the word hence, they're saying, like, look back, there's a reason we made you do the first part. So now consider the functions f of x and g of x. Here are the graphs. So we've got f and g. Cool. Then the shaded region R is enclosed by f, g, the y-axis, and x equals 1. So it's just that shaded bit right there. First of all, write an expression for the area of R. So that expression, all I'm doing is I'm going to take an integral, right, because we want an area, and it's going to go from 0 to 1. And the 0 to 1 is because those are the x boundaries of it. And then my upper curve right here is g. My lower curve is f. So g, which is this, so we're going to have 6 minus 3 x squared x cubed plus x minus f, which is going to be this one, which is the square root of x cubed plus x, all of that dx. That right there is your answer for 1c. It is the expression for the area. Then it says, hence, find the exact area of R. Now, if you plug this into your calculator, I'm pretty sure you're going to end up getting a decimal. And so when they say exact area, they mean that you got to kind of go through and do all of the work. So there's a reason this is all one problem. Pay really close attention. This does not look like 1b, or it does not look like 1, but there's some similarities, right? We've got that square root of x cubed plus x that's kind of in there, and we've got that 3, and then hey, I've got 2 of these, so I want you to pay attention to this section right here, because what I'm going to do is I'm going to factor out a 3x plus 1, and the reason I'm doing that is because I see it up here, and I'm like, okay, if I take out a negative, then okay, cool. So what we're going to do is we're going to rewrite this, and this is getting to 1d. I'm going to rewrite this as 6 minus, and that minus is just taking care of this minus and that minus. And then here, 3x plus squared plus 1 times the square root of x cubed plus x dx. And then things are way better for us because now we know how to deal with this. I know from part 1b what the antiderivative of this section here is. If you look, and let me find another color so we can highlight this for you. So like this right here, the antiderivative of this is here. And so I already have that. And then the antiderivative of 6 is no problem at all. That's just 6x. So this is going to be equal to 6x minus 2/3 x cubed plus x to the 3 halves plus c. But I don't really have to mess with that plus c because this is actually a definite integral, and I'm just going to go from 0 to 1. So we're going to evaluate from 0 to 1 here. Okay, getting that exact answer then. Here we have 0 for the whole thing, and this is just going to give us 6 minus 2/3 times 2 to the 3/2. 2 to the 3/2 is going to be 2 cubed would be 8, and then square root, so you'd get 6 minus 2/3 to the square root of 8, and that's the same as 6 minus 2/3 2 root 2, so that is the same as 6 minus 4 root 2 over 3. There's your exact answer. Okay. Here what we have is we have a second derivative, and it wants the original function, so it's given us 2 starting values. So first we need the antiderivative of 15x to the 1/2 plus x plus 1 to the negative 2 dx. So I'm just going to find the antiderivative here, antiderivative here. Please note, this is technically a u substitution problem, but I can kind of skip it because the derivative of the inside is just 1, and that will work out very nicely for us. If this had like a 2 or a x squared, then I would need to do some extra work. But in this case, we're going to take advantage of that. So antiderivative here is just going to be 15, and then x to the 1/2. We'd have x to the 3/2 over 3/2, which we'll clean up in a second. And then this is just going to be x plus 1 to the negative 2 plus 1 all over negative 2 plus 1. We'll add those together, plus c. Don't forget your plus c, because that's actually one of the reasons that we needed 2 of these. Let me get a little bit more room here. Okay, so this is the first antiderivative. Now we need to take the antiderivative of that, and I'm going to clean it up just a titch as we're doing this. So this would be 15 times 2/3. Got that, we'd get a 5, so this is just going to be 10x to the 3/2. This part would get us just a negative, and then we'd have x plus 1 to the negative 1 plus c dx. So this was the first one, and now we're needing to do it again because we went from f prime prime to f prime, and we want to get all the way back to f. Okie doke! So this guy right here is going to be 10x to the 5/2 over 5/2 minus, and in this case, now remember, if we use this same rule, we'd have negative 1 plus 1, and we'd end up with a 0 in the bottom, so that's not going to go well for us. But it works out pretty nicely that this is just the natural log of x plus 1 plus cx, because remember, antiderivative of just any old number would be that with an x, and then I'm just going to add plus d. So this is what f of x looks like. But now we need to solve for c and d, and I think it'll help a little bit if we just clean things up to begin with. And by clean things up, I mean this 10 nonsense over here. So 10 times 2/5 would be times 2. That just got us 4, so now we have 4 x to the 5/2 minus the natural log of x plus 1 plus cx plus d. That is f of x. Now what we can do is we can start using some of those boundary conditions. So when f of 0 is negative 4, so what we get if we plug in 0, well, here we'd have a 0, and the natural log of 1 is also 0, and that is 0, so we just get that d is going to be equal to negative 4. Okay. And then the other one said that f of 1 is 0, so here we just get 4 minus the natural log of 2 plus c minus 4 is 0. those 4's are going to simplify for us, and then we get that c is the natural log of 2. So our final function is this. I really enjoy this one. So first they tell you that f of x from negative 2 to 2 is 10, and from 0 to 2 it's 12. That implies that if you're actually going to look at the function itself, so we've got negative 2 all the way up to 2, that somehow the area under the curve, so if it was just like this, that area would have to be 10, except they're also telling you that this area would have to be 12, which means that we've got to have some negative area over here. And in fact, the sum of the area we can find out pretty quickly, because if we wrote it out, the integral from negative 2 to 0 of f of x dx plus the integral from 0 to 2 of f of x dx, that has to be the integral from negative 2 to 2 of f of x dx. Well, we already know this bit here is 10, and we know this bit here is 12, which means this has to be negative 2 in order for this equation to work. So the function itself probably looks a lot less like this, so this is probably a bad picture, and it's going to end up looking a lot more like some negative area and then a bunch of positive areas, so maybe like that. It doesn't have to be exactly like this, obviously, but if this is negative 2 and this is 2, but something similar to that. Okay, and that actually answers our first question, which is negative 2 to 0. What is that? That is equal to negative 2. Just kidding. The question that was there, sorry. The question is if you took the function and added 2 to everything, then what would you get for that section? So here's how we're going to solve this. We're going to treat this like it was 2 separate integrals. So this guy down here, negative 2 to 0 of f of x plus 2 dx, and then we do have the parentheses around the whole thing, but that is the same thing as negative 2 of f of x dx plus negative 2 to 2 of 2 dx, right? Just like if this was x plus 2, you could take the antiderivative of x and the antiderivative of 2. Well, this one we happen to know is negative 2. And this would just be 2x, in which we would evaluate from to 0, my bad, negative 2 to 0. And we're going to add those together. And doing so, here we'd get 2 times 0, which is 0, minus 2 times negative 2, which is negative 4, but this is negative 2 plus the opposite of negative 4, which would get us 2. Good gracious. It's fun. Okay. Second part says negative 2 to 0 of f of x plus 2. But in this case, notice that plus 2 is within the parentheses. So it's like you literally took the x values and added 2 to them, which you could think about of like taking the whole thing, the whole graph, and just like shifting over 2's, like go over 1, 2. The entire thing is just going to like shift over by 2. So it's really going to end up being the same thing as negative 2 plus 2, 0 plus 2 of f of x dx, which means that you just have the integral from 0 to 2 of f of x dx, which is just going to be 12, because they told you that in the original problem. Voila. Okay. Here we've got f, and we want its derivative, and we've got g, and we want its derivative. Both of these would require the product rule. And if you just look at my notes here, this time I'm going to cheat a little bit, just because it's only the product rule. F prime is e to the negative x cosine of x minus e to the negative x sine of x. And g of x ends up being e to the negative x, g of x prime, e to the negative x, negative sine of x minus e to the negative x cosine of x. Then we've got that sneaky hence. Again, it says hence or otherwise, meaning there's going to be another way of doing it, but this was their hint to you. Hence, find the antiderivative of e to the negative x sine of x. Well, I'm seeing that appear a whole bunch in here. So I'm going to see, and because I've got a positive here and I've got a negative here, what's going to happen if I add these together? If you do that, what you'll find is that we've got a positive e to negative x cosine of x and a negative, so those are going to simplify, and you are just left with negative 2 e to the negative x sine of x, which means that this function right here is just a scalar. Like if we add these functions together in the original, it will give us the derivative. In other words, that if this is the original function, which is f of x plus g of x, that the derivative is just going to be that negative 1/2 to deal with this negative 2 e to the negative x sine of x. In other words, that the integral from e negative x sine of x with a multiplier of negative 1/2 would get us the antiderivative. Negative 1/2. That, which we could then just evaluate from 0 to pi. 0 to pi. Which looks like here plugging in pi and here plugging in 0. We would get negative 1/2 e to the negative pi, and then sine of pi is 0 and cosine of pi is negative 1, and then we're going to get a plus just from this negative here. 1/2, because e to the 0 is just 1, and cosine of 0 is 1, so we just get to get 1 times 1 times negative 1/2. And so this right here, we're getting pretty close here. This negative and this negative are going to kind of simplify for us, and we are just going to get 1/2 e to the negative pi plus 1 as our final